Okay, Assalamualaikum. Hello. So we continue our study on efficiency and regulation of the line. Okay. So before I continue, make sure you slide in your attendance and make sure you submit your assignment 1. Okay. And of course, assignment 2 already available in e-learning. Okay, you can start doing it. Okay, you are given 4 weeks to complete it. And there is also a feedback. Make sure you submit your feedback for chapter 2. Okay, so we continue with efficiency and regulation. Okay, voltage regulation. Okay, in general, phases of the voltage and current at the sending end of the transmission line can be represented as this one. Okay, so at the receiving end represented as this one. Okay, as you can see here, the difference is here at the receiving, where we use the receiving voltage as a reference, 0 degree. Okay, so make sure you know that this is 0 degree. Another one is varies. Okay, in most cases, phasor voltage at the receiving end is taken as a reference. Okay, this one already explained to you. Okay, and the total apparent power from the source, okay, is SS. Let me check the recording first. Okay, the total apparent power for the source is S is equal to 3 Vs Is. Okay, conjugate. So if this one is the complex power, you have to use conjugate. And don't forget to multiply by 3 because this is a 3-phase system. I think this one is wrong, and this is not the apparent power. This one is a complex power because you have conjugate here. Okay, and this is a complex answer. So this is, let me change this. Okay, this one is total complex power. Okay, and complex power. Okay, so you can see here there is an angle there, means that this is a complex power. So this one is 0 degree, so just use the I. Okay, negative I. Okay, remember we use VR as a reference, it becomes 0 degree. Okay, so just negative angle of IR. Okay, the real power magnitude delivered by the source and the receiving by the load is PS is equals to real of the apparent power, okay, or 3. Okay, so if you already calculate the complex power, make sure 3. Okay, many of you forget about 3 because of the 3 phase. Okay, so 3 Vs Is cos theta Vs minus theta Is. So this is how to calculate power, real power. Okay, for the real power at the receiving, just cos theta IR. Actually negative theta IR, but cos is usually doesn't care about negative, so you can just put negative IR. So this one is just revision from your chapter 1. Okay, so you want to know what is the power loss. Okay, so just power loss is PS minus PR, power sending minus power receiving. Okay, so this is also simple. I think you know the power loss is the calculation of the power losses. And of course the efficiency, receiving divided by sending. Okay, output divided by input. Okay, so make sure you know this is just a standard efficiency formula. Okay, and of course you can multiply by 100 to represent it in the percentage. I think this one is simple because you already know how to calculate efficiency. This is just the way to do it. And make sure efficiency, you cannot use the complex power. Efficiency, we only look at the real power. Apparent power, we don't look. Okay, only the real power for efficiency. Okay. Okay, so we move on to the next part, which is voltage regulation. So, of course, usually when it comes to transmission line, we have to look at efficiency and how well the transmission line can regulate the voltage. Okay, so voltage regulation is the degree of voltage rise at the receiving end of the line when the rated load is completely removed from the terminal with the sending voltage is fixed. Okay, so what is this mean? Okay, where is it? Okay, so you have a Vs here. Okay, you put Vs maybe 275 kV for example. Okay, okay, and okay, let me check the recording first. Okay, so I think the definition is wrong actually. Okay, okay, let me just explain it first and we see after this. Okay, so assume this is open load. Okay, no load. Okay, no load is connected. Okay, this one you have a resistor, inductor. Okay, you have the capacitor. Okay, this one is just more simple. Okay, because I sending is equals to 0 means that Vs, okay, Vs is V receiving is also equals to 275 kV. Okay, because there is no voltage drop here. Because of the current is 0, voltage is equal to VRL is equals to 0 means that Vs is equals to VR, okay, plus VRL, but this one is 0, so just equals to VR. So this is at no load. Okay, let me remove this. But at full load, okay, at full load, okay, at full load, you have value here. Okay, you have a value is. So VR is not equals to 0. Okay, so this one not equal to 0. So there is a voltage drop. So Vs is equals to VRL plus VR. So basically they will be different. So this one VR is probably 270 kV. Okay, depending on the load and everything. Okay, this one is too much I think. Voltage regulation is only a small number. Okay, so that is means by voltage regulation. Okay, so how to do this? We look at the rated load. Okay, rated load means that the full load. Okay, for example, full load of the transmission line. Okay, transmission line has maximum capability. Okay, so at full load, for example, this one given as 50 mega MVA. Okay, so basically 50 MVA is the full load. Okay, basically the full load means that the maximum capability of the transmission line. And of course the formula for voltage regulation VR, okay, voltage regulation is voltage at no load, okay, at the receiving you look at the receiving end, no load minus, okay, this one only take the magnitude, okay, don't take the angle. VR at the full load, okay, divided by VR at full load, okay, only magnitude. Okay, so here is some example. Okay, assume that the phase voltage and current of the load terminal is this one. Okay, so let me take a screenshot here. Okay, so you can calculate the efficiency, of course, using the formula square root of, okay, 3 VR IR. Okay, so this one is, okay, if you look here, efficiency, okay, should be 3. Okay, okay, this one also needs to be careful. Efficiency, okay, efficiency is equals to 3 VR IR, okay, only the magnitude, cos theta IR divided by 3 VR, okay, I says VS IS cos theta VS minus theta IS. Okay, so this one is cancelled. Okay, so no need to worry. But for this one, okay, actually also cancel. I think this one no need to worry also because you cancel it. Okay, so we continue. Efficiency. So just use the formula. Okay, so you just take the receiving end. Okay, efficiency is equals to VR IR, okay, cos theta IR, okay, divided by VS IS cos theta VS minus theta IS. So make sure you know the formula. Okay, you have to memorize it. So VR is, just take the magnitude, 5773.5. Okay, this is the only the magnitude. Cos only and then the current 32 point, okay, 32.1. okay, cos theta IR is this one, cos negative 25.8 divided by 5916.6 angle, no need to angle, 32.1. That's why here we don't see this, because you can cancel this. Cos theta B is 0.7 minus 25.8. okay, so make sure you use the minus and minus. Okay, and if you calculate this, you can get 0.98 or 98%. Okay, that is how you calculate the efficiency. Okay, it's quite simple. How about voltage regulation? So voltage regulation is also simple. So VR is equals to V at no load minus V at full load, okay, divided by V at full load, and all of it is receiving, okay, at the receiving. Okay, so V at the receiving at no load is basically VS. Okay, remember that I say, okay, so VR at no load is basically equals to VS. Okay, make sure you know this. So 5916.6, this one, sending voltage, minus the full load voltage. Okay, you have to use the full load. Okay, don't use the half load or and everything. So you have to use the full load. 773.5 and then divide by the same one, 5773.5. So this one and this one is the same. So you get 0.025 or 2.5%. Okay, so voltage regulation, okay, and transmission line. For transmission line, okay, efficiency is quite high. Okay, usually more than 90. Okay, that is for efficiency, and the voltage regulation are usually less than 10. Okay, very small. Okay, and the efficiency is very high. Okay, so let me clear this first. Okay, here is another example for the T circuit. Okay, medium line. Okay, T representation, three representation. Okay, for the T circuit. So you can see here IR and IS is not the same. Okay, for T circuit, the current is not the same. Okay, because of the capacitor of the admittance. So of course you just use the formula again. Make sure you know the formula and you get the efficiency. And voltage regulation, you can use the, okay, let me check the recording first. Okay, so you can see here the T representation. Let me draw the T representation back first. So something like this. Okay, capacitor. Okay, make sure you know how to draw this. Okay, so you can see here, and you have Vs. Okay, you have Is. Okay, this is I R. Okay, this is V R. Okay, when there is no load, okay, this is open circuit. Okay, when there is open circuit, IR is equal to 0, but IS is not equals to 0. For medium, IS is not equals to 0 because you have the current here, I Y. Okay, I at Y. So because of this, you have to calculate VR at no load. Okay, how to calculate VR at no load? Okay, this one is 0, so basically you have to calculate the voltage here. Okay, so how to do this? Okay, so you have to look back what model you use. This is the T model, and recall back the formula for T model, this one. Okay, so you can see here Vs is V sending is equals to this one. Okay, IR is equals to 0, VR we want to know. Okay, so let me extract the formula first. So Vs is equals to 1 plus 1 divided by 2 yz. Okay, VR, okay, plus z plus yz squared divided by 4 IR. And remember, IR is equals to 0. Okay, so this one is equals to 0, so you only take this information. So VR is equals to, from this, okay, this one is also equals to 0 lah, because 0, anything that multiplied by 0 is equals to 0. So Vs 1 divided by 1 plus yz divided by 2, or you can simplify this more, is basically becomes, okay, Vs 2 divided by 2 plus yz. Okay, so that is how you find the no load voltage at the receiving. So let me move this back. Okay, so you can see here VR is basically VR no load. Okay, VR no load, this one is here, equals to Vs z, not z, this is 2 divided by 2 yz. Okay, so use this formula to calculate. Okay, and make sure you include the angle here. Okay, and include here, this one Vs is angle 0, this one is angle 0, that's why there it doesn't show the angle. So after you calculate VR at no load, okay, this one, okay, So 17712, okay, this only take the magnitude, okay, don't take the angle. I repeat again, only for voltage regulation, only take the magnitude. And at the full load, you can use this original value, this one, okay, 1720, 173 to 0.5. So this one is at the rated voltage, okay, at the rated load. So this is how you calculate it. Okay, the first one is easy. Okay, you can see here. The first one, you just take the Vs because this is a short line. Okay, be careful in the voltage regulation for short line. Okay, short line and medium line. Okay, VR no load is equals to Vs. Okay, for short line. But for medium line, you have to derive either T model or pi model. Okay, just use the formula and make the IR equals to 0. Okay, for pi model, okay, so you can see here pi model. Okay, also the same, IR is also equals to 0. Okay, I think no need to draw it back, you already know. Okay, just make IR is equals to 0 and then you can get the VR. Okay, VR no load is equals to something Vs. Okay. Okay, how about long line? Actually, long line is out of your syllabus, but for efficiency, you also can calculate using the formula. So this one no need to worry, but the voltage regulation is much more complicated for long line. So for this one, probably you can avoid this. Okay, no need to worry on this. But the formula for voltage regulation is the same also. Only the problem is how to find the voltage at the receiving end at no load. So if you want to memorize this also can, but usually it doesn't come up. So the voltage Vs is divided by cos YL. Okay, this one is out of your syllabus. Okay, and also you can see here the voltage regulation is quite bad. Okay, so efficiency higher is better. Okay, but for VR voltage regulation, lower is better. Okay, so this one is actually very bad. Okay, for long distance, the voltage drop is quite significant and it is very bad. Okay, I think okay, that's it for transmission line. Okay, so next week we will learn about the distribution system. Okay, so if you still cannot find way to calculate your assignment 1, okay, actually the assignment 1 is basically based on the third part of the topic, okay, which is distribution. Okay, so you can try to look at this. Okay, look at this earlier. Okay, you can look how to do the calculation. Okay, that's it. I just want to remind you the test. Okay, test 2 will be conducted soon. Okay, so prepare for test 2. Okay, let me open the e-learning here. Okay, so for test 2 here, you can see that test 2 will be conducted on 10 January 2022. Okay, of course at 9 p.m. 1 hour and 15 minutes. Okay, the time will be given soon. I'm not sure whether it is 1 hour or 1 hour 15 minutes. And the topic cover is the power system generation and transmission. So basically these two topics, generation and transmission. Okay, focus on these two topics. Okay, for test 2. And also don't forget the feedback. Okay, fill out the feedback. Okay, submit the assignment, this one, and you have a new assignment, application of electromagnetism, and you have to submit it before 15 January. Okay, I think that's it for today. We will meet again next week.